Good day, I'm Dr. T and welcome to my office. So today I would like to talk a little bit about how we represent the way in which electrons are organized within the atom. And one way of doing this is known as an orbital diagram. Orbital diagrams utilize a series of boxes. Each box represents an orbital, and these orbitals can hold, as you remember from earlier videos, up to 2 electrons. Now the boxes are listed vertically in order of energy. So on the bottom we have the 1s orbital, which is the lowest energy. An electron going from outside the atom and joining a 1s orbital would lose the most amount of energy when it goes into this. For this, the top of the graph, the very, very tip top, would actually be 0 energy. The amount of energy an electron just floating free, not attached to any atom, would have. Now, starting on the bottom, we're going to have our 1s, because it's the lowest energy of the orbitals. Above that is going to be the 2s, then the 2p. Now, you'll notice it's not one box for 2p, because remember, there are actually 3p orbitals. So there are 3 boxes. They're at the same level. Orbitals of the same type are known as degenerate. This doesn't mean that they are somehow morally corrupt. It means that they have the same energy and they're more or less interchangeable. Above that now becomes the 3s, the 3p, and you would think I would say the 3d above that. But the d orbitals tend to be fairly high energy orbitals, so it's actually going to be 4s, then 3d, then the 4p. We can continue with a similar pattern with the d's coming in between the s and p of the shell above it, and the f's actually going a full 2 shells. Difference. Now, let's start filling these things with electrons. Electrons are represented in chemistry as a single-headed arrow, or a single barbed arrow. With each box, we're going to put in 2 arrows. Now, we're going to put the arrows representing their spin. It's not really implied which spin is which, it's just saying that up is one spin and down is another spin. Since an orbital can only have electrons going in opposite directions, we have to make sure that whenever we put an up spin arrow in an orbital, we then put a down spin arrow for the other electron in that orbital. Once again, up and down can be clockwise, counterclockwise, vice versa. It doesn't really matter in this case. Now, when we come to the p orbitals, as we're filling these, we actually have a couple more choices. The s orbitals are fairly straightforward. You put one in, then you put your other in, and then you move up to the next layer. But with the 6th electron being added, now comes the question. Do I put the second arrow in the same box and give it a roommate, or do I separate them out? If I separate them out, do they go opposite or parallel to each other? The answer is the latter. You separate arrows out so that electrons fill orbitals one at a time. The idea here is, imagine, if you had apartment choices, you'd prefer to not have the roommate. And the electrons are the same. Additionally, they tend to coordinate their spins in the same direction. So if I was to fill, say, 6 electrons, which would be the ground state for carbon, because remember he has 6 electrons in him, then the first 2 would go in 1s orbital, the next 2 would go in the 2s orbital, and then the last 2 would both be going either up or down. Traditionally we write them as up, and they would be going into separate boxes in the 2p orbitals. Now as I add more electrons, obviously 3 boxes all going up. Once I go for the 4th electron in p orbitals, now it has to go down. And I'm going to start filling this in. And simple process, I start filling it up until I run out of electrons. Yay! Fairly straightforward. Now this is assuming that we are doing a ground state. For excited state, obviously the electrons aren't going to be in the same configuration. They can't both be up or both be down in a particular orbital, because once again that violates them trying to stay apart. They can't coexist in the exact same spot. But you can have, in an excited state, say, one electron going up, and the next box over, that electron going down. That's an excited state, not the ground state. And usually we focus on the ground state. Additionally, in an excited state, you can very well have empty boxes and have gaps in this, because that's what's making it an excited state, those gaps. Now, when it comes to these orbital diagrams, that's a lot of stuff to write. And quite often we want that information, but we don't really want to go through the entire process of writing out the entire orbital diagram. So we don't. There are a couple of shorthand ways of doing this. And typically, once again, we're looking at the ground state configuration of these atoms. The first way is to basically collapse this orbital diagram. We still keep the 1s, and then instead of drawing a box with 2 arrows in it, we do a superscript 2 above the s. Then we have the 2s, and we put it right next to it, and put a superscript 2 above that s. And then we have the 2p, and saying all the p orbitals are full in this case, we could put 2p, and saying that there are 6 electrons in there, we would put 2p superscript 6. Continue in this pattern until you have completed however many electrons you're putting in there. You can shorthand this in a couple of ways. For starters, if you've got both a 2p and a 2s, well, you could just simply put 2s2p6, or however many is in your p. This shorthands what you're doing, a little bit less to write. Additionally, if you do the electron configuration, which is the shorthand notation of what we're doing, for a noble gas, you'll notice that it's a pattern. Elements that are heavier than a noble gas, or have more electrons, I should say, than a noble gas, will have the electron configuration of the noble gas right before them in their configuration. So we can shorthand this by saying bracket, whatever symbol of the noble gas in question is present, and close bracket. These are going to be square brackets. And then continue on with whatever else you happen to be adding to it. Okay, let's say we want to find our electron configuration without doing an orbital diagram. Or even if we are doing an orbital diagram, honestly, that's kind of the hard place to start with. So we have a couple of options. First, you can memorize the order of energies for each of your orbitals. So 1s2, 2s2, 2p6, so on and so forth. Continuing until you run out of electrons. To help with this, a lot of textbooks will show a graphic, as I'm showing over here, that gives kind of a visual version of a mnemonic, whatever you would call that, as to remembering the order that those shells are going to fill. Alternatively, we can use a periodic table. Now, to do the periodic table, we've got to know a couple of key features. First, your periodic table is divided into blocks. These are areas where a certain type of orbital more or less dominates the chemistry. So if you look at the alkaline earths and the alkaline metals, in both of those cases, that's in what we call the S block. And helium is actually going to move over and pretend it's sitting above, have to look, beryllium. Yeah, I got half of it memorized, not the other half. Okay, so helium's sitting above beryllium, at least in our mind. Yay. Now, the transition metals, of course, the dip in the middle, that is also what we call the D block. This is a case where the d orbitals are dominating the chemistry of that particular block, and yay. The p block is next to it, and this, of course, is the p blocks dominating the chemistry of that particular, or the p orbitals dominating the chemistry of that particular block. On the bottom, we have the F block, and you guessed it, that's the F orbitals. Now, I'm generally going to try and stay away from the F block because they have a lot of exceptions, as in there are more exceptions to the rules I'm about ready to tell you in the F block than there are not exceptions. So let's just ignore the F block altogether. Another quick point. Lanthanide and actinide, those are actually D block. It's going to make things a little bit interesting when we get down low. Okay, so what we can do is use the periodic table as an abacus. Keeping in mind these blocks are going to help us remember what atoms go, or what electrons go where within your orbitals. Okay, so let's pick an atom of interest. Say silicon. Always fun. Okay, for starters, we're going to start out to the left of hydrogen. As we cross a element on the periodic table, we're going to tick up one electron. And we're going to keep doing that until we get to silicon. So we're going to cross hydrogen and helium. Those are in the S block, and they're on the first period. The first period is going to correspond to their valence shell being in the first shell. So right now we have one S2. We've got 2 electrons. They're in the S block. We have now left both the S block and the first period. So we're now entering the second period. We'll write 2. traveling through the lithium and beryllium, we'll have 2s2 now. Because we've gone through the s block, we have added 2 more electrons. We still have time to go. For these periods, there is no d block. That won't take place until period 4. So we're just going to keep going and enter the p block. You can write a 2 here if you want, or you can leave it off. So now I have p. And I'm going to go clean through boron, carbon, nitrogen, oxygen, fluorine, and neon. Yeah, I got to look on this. So that's 6 elements if you hadn't counted quick enough. So P6. Now, we've left that period and we're dropping down to the next period. So put down a 3. We're crossing through neon and magnesium. S2. Now we're going into the P block because once again, the D block doesn't extend up to this point. The third shell does have d orbitals, but they'll remain empty until there is actually a 4th shell starting to fill. Okay, so we cross into aluminum and silicon. Wait, didn't I say we were stopping at silicon? Yeah, I think I did. So we're stopping at silicon. That's only 2 elements in, so we're going to say P2, not P6 because we didn't go clean through. So finally, my conclusion is I have 1s2, 2s2, P6, 3s2, P2. So we've completed silicon. Now, let's do a quick test. Why don't you do the electron configuration for neon? I'll wait. You done yet? You know you can pause the video, right? Okay, let's do this. So for neon, that's shown here. You'll notice how the ground state electron configuration for neon is actually contained within that of silicon. We could use this to our advantage. And let's do that because, hey, advantages are nice. So what I'll do is I will shorthand the way silicon is written. Instead of writing out the whole thing, or even instead of starting from the beginning of hydrogen, I'll start from neon. So I'll do bracket, a square bracket in this case, Ne, close my square bracket, and then I can put my valence shell, the 3s2, P2. Yay! I've shorthanded it. Now, I can use this to my advantage when doing the electron configuration of other atoms, especially ones that are somewhat larger. This way I don't have to go through the entire periodic table in order to get down to some of the heavier ones. So let's start off with something kind of mid-difficulty. How about gallium? Okay, so with gallium, I first look for my noble gas that is as large as possible, but without going over. So Price is Right rules. In that case, it is argon. So I will do square bracket, Ar, close square bracket. Now I am starting not in front of hydrogen, but in front of potassium. And I'll continue on very much as I did beforehand. So I'm in the 4th row, so 4s, 2, because I've gone through potassium and calcium. I've yet to reach gallium, so I'm going to start moving in. Oh look, we actually have our d orbitals now. These are the same as the 3d orbitals that we kind of omitted to use previously. So we're moving into the 3d orbitals. When you transition into the d block, subtract 1 from your period number to know what your shell number is going to be for the d orbitals. So now I do need to write 3d. Now I'm going to go through the d block, and there are 10 elements in the d block for period 4, or the 3rd shell. So yeah, I'll let you look at these things. Zoom through that, 3d10. Now, I'm going back into the P block, and therefore, 4p. Once again, that dip only applied during the D block. I go to gallium. Hey, that's what I'm looking for. So, 4p1. Typically, to clean things up, we rearrange these things in numerical order. So I would say bracket, AR, close bracket, 3d10, 4s2p1, even though the energy is not in that order. Now, there are a couple of interesting quirks when it comes to the D block. Let's take a look at copper. So, if you were to do the ground state electron configuration for copper, actually, take a minute. Once again, you can pause this if you need to. Okay, you got it? So you probably found that the ground state electron configuration for copper was 4s2 3d9. However, if we actually experimentally determine it, we realize that it's actually 4s1 3d10. Wait, what? Turns out that there's a major exception to the rules we've been describing, and that comes if you're in group 6 or 11. In this case, you have a d orbital that is either almost half filled, so 4 out of 10, or almost filled, 9 out of 10. In either case, it's actually the energy levels start to get a little bit fuzzy, and it is a somewhat lower energy for it to be half filled and take one of those electrons from the s orbital. Yay, don't you love exceptions? They're so much fun. If you wanted to, you could start doing the ground state electron configuration of every element on the periodic table. Or you could just go download the periodic table that already has that on there for you because, it's not like you're the first person to do this. You would notice a couple of interesting trends. The valence shell, remember that's the outer layer of electrons, not the inner layer, which is very originally named core electrons, because, we're not original, will all look actually very similar. So if you look at the alkali metals, all of their valence shells are something, whatever the period they're in, S1. Seriously, run the math if you want to. They're all that. If I look at the halogens, the valence shell, once again, change the period, but those will always be something, S2P5. Remember that these columns mean something? This is why. The chemistry is very similar because the electrons in their valence shell are arranged in very similar ways, and thus will behave in very similar approaches. With that said, have a wonderful day.